So, good afternoon, everyone, and welcome to this lecture. This is lecture number 1, and we are starting off with electric current. And this is probably the part where we should go very quickly because almost everything, apart from small things, we have already discussed in the previous topic. That was capacitance. We have almost discussed everything. Just a small part which is at the beginning of the chapter and which is at the end of the chapter. That is what it is remaining. So we are not going back into series and parallel combination. I think we have done enough of that. Yes or no? Do we remember it? Or it has gone in the past and you have forgotten it? Do you remember what we have done series parallel that told over
Yes,
the
sir. Yes, sir.
we are not going all those circuit solvings and all because we are already done with this. So we will move ahead and see what we have not seen. And what we have not seen is what we are starting with. And the first thing is electric current. What do you mean by electric current? Yes. First, what do you mean by electric current? No one knows it. Electric current.
Flow of electrons through negative terminal to positive terminal.
Electric current is the rate of flow of charge. The rate at which charge flows per unit time with time. That is known as electric current. Electric current is normally denoted by the letter I. What type of quantity is electric current? What type of quantity is electric current? What type of quantity is electric current? Anyone? Scalar or vector? No one knows it?
Scalar, sir.
The scalar quantity. But it is a very peculiar type of scalar quantity because this electric current has magnitude. It also has a direction. We'll see the direction as well as the magnitude, but it is still a scalar quantity. Why it is a scalar quantity?
Not for
Hmm? It is a scalar quantity because it does not obey. It's a scalar quantity because,
Vector law of addition, sir.
yes, it does not obey vector law of addition. And therefore it is not treated as a scalar, it's not treated as a vector quantity. It is treated as a scalar quantity, and we have already seen its example. If for example, if there is a node and there are some currents or a junction and some currents are coming in and some currents are going out, we simply write them algebraically. Kirchhoff junction law. Do we remember this? I1 plus I2 will be equal to I3 plus I4. We don't add them vectorly. Current does not get added vectorly, and that for this simple reason, current is a scalar quantity. Do we understand this?
yes, sir.
The SI unit of current, you can call it coulomb per second, or that becomes ampere. And ampere or A is one of your 7 fundamental units. Do we remember those 7 fundamental units? One of the 7 fundamental quantities is one of the 7 fundamental quantities. So that is your current. Now, since we talked about the direction of current, we must also see what is the direction of current taken as. Normally, in a conductor, what happens is electrons will flow. Yes or no? Current is the flow of electrons. In a conductor, there are large number of free electrons and they flow. But The direction of current is not taken as the direction of flow of electrons. It is taken as the direction of flow of what? As you can see, this is the direction of current that is drawn. And you can see it is taken as the direction of flow of electrons. No, it is not taken as the direction of flow of electrons. It is taken as the direction of flow of positive charges. Positive charges actually do not flow in a conductor, but still the direction of current is taken as the direction of flow of positive charges, and which flow in the direction of electric field, and therefore current always flows in the direction of electric field. That is the direction of current, and therefore it always flows from a point of higher potential to a point of lower potential. Do we remember this?
Yes, sir.
Yes, sir.
Current always flows from a point of higher potential to a point of lower potential. If we talk if we talk about this in terms of electrons, which are the actual charge carriers or actual current carriers, the direction of current is actually opposite to the direction of flow of electrons, though in reality it should have been the direction of flow of positive charges. Do we understand this? So as you can see here, the current is going like this, the electric field is directed like this, but our actual charge carriers, actual current carriers, they are moving in the opposite direction. So electrons basically flow from a point of from a point of lower potential to a point of higher potential. Do we understand this? So that is taken as the direction of current. Do we understand this? Yes or no? No, yes.
Yes, yes, sir.
Everyone understands this? Yes or no?
Yes, sir.
Have we noted it down?
Noting, sir.
Note it down. I'll give you 2 minutes to note it down.
No, sir.
Done, sir.
Okay. So, one of the 7 fundamental quantities we have seen. Now, whenever we talk about electric current, we always say that it is the rate of flow of charge. Yes or no? But actually, it should be considered like this. It should be the rate of flow of net charge. What do I mean by net charge? For example, if there is a conductor like this, a random section of a conductor I have taken, and if I take any cross section area of this conductor, you might have some electrons or some charges moving like this. You might have some charges moving like this. Now, even though charges are flowing, there may not be any net flow of charge. So whenever we talk about current, we talk about the net flow of charge. So remember, current is the rate of flow of net charge. Current is the rate of flow of net charge. Net. There must be some net charge flow. Now, whenever we talk about current, we might talk about 2 types of current. And the first type of current is known as average current. Average current I in a dabba, and this I in a dabba is similar to what we had seen previously in chapter number 1, which I think you are revising these days. Average current is exactly same as your average velocity, something of that nature. What would be your average current? What would be your average current? It will be total charge divided by total time. Now, whenever I say total charge, you must remember that it is the net total charge. Don't worry, we will do some questions on this that will make you understand this. So average current, I average or I in a dabba, is delta Q total charge divided by total time. Do we understand this? Do we understand this? Are we there in the class? Everyone is chilling out. No one is there. Okay. So average current is total charge divided by total time. Then I have the next definition, which is instantaneous current. Instantaneous current is current at any particular time. Right now, what is the value of current? That would be known as your instantaneous current. And how will I find instantaneous current? Instantaneous current I will be rate of flow of charge dq by dt. Yes, everyone is there or no? I've lost them. All of you together at the same time. Am I audible? Am I visible? Am I talking to someone on the other side, or I'm just babbling things on my own?
You are audible and visible, sir.
You are able to follow what I'm saying here. Everyone is able to follow what I'm saying.
Yes, sir.
Yes, sir.
Okay. Current is rate of flow of charge dq by dt. I can write this equation in a different way. dq will be equal to I into dt, or the total charge flown can be written as integral of I dt. I hope I am making sense here. Yes or no? I'm making sense.
Yes, sir.
Okay. So I dt ka integral will give you the total charge. Remember, there must be a net flow of charge for current to be considered in a conductor. If there is no net flow of charge, we don't consider any current flowing, even though there is a flow of charge. If there is no net flow of charge, current is said to be zero. Two types of current: average current and instantaneous current. I hope we are able to understand and digest this one. Yes or no?
Yes,
Yes,
sir.
sir.
Have you noted this down?
Noted,
Huh?
sir. Done, sir.
Okay. Now, what do I mean by net current? We will try to understand this with this particular example. 10 electrons move from left to right, and 5 protons moved from right to left in 5 seconds. Find the average current in the wire. I hope you remember what is the charge of an electron and the charge of a proton. Yes or no?
Yes, sir.
Yes, sir.
You have to also find the direction of this average current. And I'll give you 2 minutes to do this. 2 minutes are more than enough to do this. Seems like I have to step in. Remember, it's a simple question, but I don't know where we are wandering. Okay, how are we supposed to solve this one? I draw this revolutionary conductor. And in this conductor, 10 electrons are moving from left to right. Ding, 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 ding. These are my electrons. 10. Ding, 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 ding. They are moving like this. My 5 protons also are doing same thing. 5 protons are moving like this, dung, 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 dung. Now I have to find out the current. How will I get it? First of all, tell me what is the direction of current here? Left to right or right to left?
Right to left, sir.
Right to left, sir. That's correct. The direction of current is from right to left. Now you have to tell me what is the net flow of charge from right to left. What is the net flow of charge from right to left? How many electrons are flowing from right to left, or how many protons are flowing from right to left? That is what you need to do. And it should not take rocket science, because this is a question of third standard. Trust me, this is a question of third standard, because in third standard you understand what is a positive number and what is a negative number. So in third standard you should be able to find out this. What is the net flow of charge, beta? Net flow of charge.
I, sir.
Take a deep breath.
Mine, sir.
Deep breath. Open your eyes and look at the universe. And in our universe, protons have positive charge and electrons have negative charge. In our universe. Say in this is the good universe to live in. Yes. Now think. In our universe, what is the net flow of charge? In our universe. Staying in our universe. Newton laws are valid. Ohm's law is also valid. V is equal to IR. That universe. Yes. What is the net flow of charge? What is the net? How many net charges are flowing and from where to where? Simple question. Don't give me, just give me the answer of how many net charges are flowing from where to where. No one knows this?
I, sir.
Okay, I'll tell you. So difficult question, I think. 15 protons are flowing from right to left, or 15 electrons are flowing from left to right. Is it difficult to understand this? No, I don't think it is difficult to understand. So you can write it in this way. 15 protons are moving from right to left because of charge on a proton, same as charge on an electron. So you can say it either ways. 15 protons are flowing from right to left, or I can say 15 electrons are moving from left to right. Do we understand this?
Sir,
Pakka na? No confusions?
no confusions.
Thank God. Now I can find out the average current flowing in this circuit. Can anyone tell me what is the average current? Do all of us understand the flow of charge? Negative charges flowing from left to right is same as positive charges flowing from right to left. Do we remember this? Do we understand this? Or it is too complicated? Understand this?
Yes, sir.
Okay. What is the average current now? Okay, you don't know it. So I have 15 electrons or 15 protons. 15 multiplied by the charge of an electron or charge of a proton. 15.6 into 10 raised to the power minus 19 divided by 5. That is my current beta. And if I calculate it correctly, I think it will be 4.8. into 10 raised to the power minus 19 amperes. That is the current that is flowing here, way less than 1 ampere. I hope I have made sense. And I'll give you 2 minutes from this universe to use and write this. Till then, I will give you another question on the same stuff. I hope everyone is noting this down. Yes or no? Everyone is noting this down.
Done, sir.
What is the problem with your done, sir? You don't understand what is done.
Sweet, sir.
Say
Answer.
there is no point of your saying done. Okay, so here it comes the next one, and I hope we can do better justice to this one. And remember, we have to stay in this universe only. Don't wander anyone else. I know that you have got ticket to wander in the universe, but let us stay in this one and try to do this one. These are the type of questions that may appear in your examination hall. These are definitely not questions of JEE Advanced. Somewhere around the territory of JEE Main. In a neon discharge tube, 2.9 into 10 raised to the power 18. So you can see the number of ions. 2.9 into 10 raised to the power 18 neon plus ions move from right each second, while 1.2 into 10 raised to the power electron, 10 raised to the power 18 electron move to the left per second. The charge on an electron is 1.6 into 10 raised to the power minus 19 coulombs. What is the current in the discharge tube? And you will have 2 minutes to get to an answer which looks like an answer from this universe. 2 minutes you have. Take your time. Okay, so how did we achieve the answer this time around? Tell me. Basically, you have to see what? You have to see the net flow of charge. Yes or no? Are we there? I'm audible and visible. Am I audible and visible, beta? Can't see any one of you. Am I audible and visible?
Yes, sir.
Okay. So, what we got to do in this question? Tell me. We have to find the net flow of charge. How much is the net flow of charge? How much charge is flowing from where to where? Tell me that fast.
Towards right, sir.
I am still very confused what is happening. Let me. Okay. So, the net charge that is flowing here in this question. Why I'm writing solution here? Why I should write written question here? The net charge that has flown here, these neon plus are moving towards right and these electrons are moving towards left. So I have to find out the net flow of charge. So basically, protons are moving towards right, electrons are moving towards left. Electrons moving towards left is same as protons moving towards right. That means the correct option has to be towards right. So it can be option number A or it can be option number B. The only thing I have to do now is to find out the total charge or the net charge. What is the net charge or total charge that has flown? So that will be 2.9 into 10 raised to the power 18 plus 1.2 into 10 raised to the power 18. That has to be multiplied by 1.6 into 10 raised to the power minus 19. And this much charge has flown per second. So this is net charge per second. And that is nothing but equal to your electric current. Do we understand this? Yes or no? Yes or no?
Yes, sir.
And
sir.
that is your answer. That is the answer that we will end up getting. Everyone got this? Can I have raised hand that we understand this? Okay. So we have understood the basic concept of the net flow of charge. Yes or no? We have
Sir.
understood the basic concept of the net flow of charge. We understand this.
Sir.
Okay. Now we can write the next point, and the next point would be written in the form of a diagram, and the diagram is coming up. I'm having trouble with this system today. I don't know what's wrong. Now, for example, if I have a conductor like this, this conductor has different area of cross section. This conductor may have different area of cross section. And if one current I1 is flowing in one part of the conductor, I2 is flowing in the other part of the conductor, and I3 is flowing in the other part, will there be a relation between I1, I2 and I3? Will I1, I2 and I3 be different, or will it be same? The current flowing in the same conductor may have different area of cross section. Will the same current flow in the different parts, or will the current be different in different parts? Yes,
Different, sir.
it would be different. Anyone else with a different opinion? Well, the current is going to be same beta, because you can treat them as three different resistance, and these three different resistance are connected in series, and therefore the current has to be same. So current flowing through a conductor does not depend on the area of cross section. If you have different resistance connected like this, one like this, second like this, and third like this, will the current be same or different in the three conductors? We have done so many questions on series parallel. We have done the entire circuit solving exercise, and then you tell me that the current will be different. That is of no use. So the current is going to be same. Current does not depend on the area of cross section. I hope we understand this. Yes or no?
Sir.
Please note it down. Please note it down. I hope everyone is paying attention to what is happening in the class.
Yes, sir.
Okay, so that is one thing that you have to note it down. Have you noted it down?
Sir.
Okay, noted it down?
Sir, completed.
Okay, then you can write. I mean, I've seen question based on this, where they give you these many charges are flowing per unit area, in through a unit area, through a unit time. So these are the different formulas that you can use. If there are n number of charges or n particles, each having charge q pass through a given area in a time t, then current, we have just found it out. The current will be total charge divided by total time nq by t. Now sometimes instead of giving you a number of particles, they might give you number of charges per second per unit area. Then you just multiply it by the area. Are we able to understand what I'm saying here? Are we able to understand what I'm saying here?
Yes, sir.
Sometimes they give you per unit volume, per unit time, how much charges are flowing. In that case, your formula for current becomes NQV into A, where V is the speed and A is the area of cross section. Do we understand this? These are simple formulae, and I've seen a lot of questions based on these formulae in your exam, both in JEE Main as well as in JEE Advanced. So please note this down very carefully. Are we noting it down?
Yes, sir.
Well, I am just feeling that today you are, what should I say? Your mind is somewhere else, and only your body is sitting in the class. Is that so?
Sir.
Remember, whenever you come to the class, you have to bring both the quantities in the class. What are both the quantities?
And mind.
Yes, body and mind both together should remain in the class and not wander in the universe. I also like to wander my thoughts in the universe, but right now we must uh, we must concentrate on keeping it in the classroom only. Let not our dreams fly high. Do we remember this? Do we have we understood this? Now sometimes and many a times you will come across where a charge will be moving in a circular path. I've seen a lot of questions based on this. If charge is moving in a circular path, how do you find the equivalent current? You just can do it in various ways, and these are the various ways written, and I hope you understand. You can write I as q multiplied by the velocity v, or you can write I as q divided by time, the time period of revolution. I hope you understand this. Do we understand this?
Yes, sir.
This this is not v, this is frequency. So let me just change this to frequency, because we'll confuse frequency with the velocity. Even I said v as the velocity. Q into f or q by t. So you can write it as q into v by 2 pi r. This is uniform circular motion. Do we remember uniform circular motion?
Sir.
Omega 2 pi f 1 by t, frequency is 1 by t. So these all things are taken from that thing. Very serious question has been made on this concept. So please remember it. I'll give you 2 minutes to note it down. So we have done up till this point. Now we can understand who is going to carry charge in different types of bodies. We know this. I am just giving you a glimpse of, just for you to understand who carries charge in what type of bodies. So just go through it quickly and note it down in as short as possible. In solids, basically metals, current carriers are free electrons. Do we understand this? In liquids, they are positive and negative ions. So they are positive charges as well as negative charges. In gases, again, they are positive ions and free electrons. Gas has may have a large number of free electrons. In semiconductors, which is going to come as the last part of your chapter, the current carriers are holes. What are holes and what are free electrons? We will come across these holes and free electrons in the chapter on semiconductors. And I hope to reach it soon. But looking at the progress that we are making, it looks a very blink chance of me getting to semiconductors anytime soon. So please be fast, be quick in noting down. Have you noted this down? Note it down fast, else I will not be able to cover your course at all. So please be fast. Have you noted it down? Let's move forward, sir. Three types of bodies. Note them down in very short. Conductor is the first type of body. What you have to remember about conductors? It has a large number of electrons, free electrons. When you put this conductor in an electric field, they will move in the direction of electric field, and therefore you will have current flowing, and that type of bodies are known as conductors. We know this, yes or no? Huh? Don't have to write all these points. No one is going to ask you in JEE Mains what are conductors. So you have to write everything subjectively. No, that is not what you are supposed to do. Just remember these points, because something from these points can come as a question in a objective type. Do we understand this? So you just have to note down the important point, not write the entire Ramayana. You understand this?
Yes, sir.
You just have to note down who is Ram and who is Sita. Who is Ram Bhagwan and who is Sita? Here Ram Bhagwan is free electrons and Sita Maiya is the electric field. So Ram Bhagwan is moving opposite and Sita Maiya is going that way. That is what you need to understand. Nothing else. Insulators. What are insulators? There are no free electrons, no freebies here, no free lunches, no free dinners. So these electrons cannot leave their parent atoms and they cannot move. They are also known as dielectrics. We have done a lot about dielectrics in the previous class. Yes or no? Just note down the important points. They are dielectrics, no free electrons, conductor, free electrons, they move opposite to electric field. That's it. Don't have to note down the entire Ramayana. We understand this. Do it fast.
Done, sir.
Okay, then we have to move forward in life. Then the third type of things are semiconductors. Again, it's still some more time till we get to that part where semiconductors, they lie between insulators and conductors at low temperature. At low temperature, they are insulators. As the temperature is increased, they start to behave like conductors. That is all you need to understand right now. Don't write the entire Ramayana, because the entire Ramayana is going to come in a different chapter altogether. Here we just need to understand when temperature increases, they behave as conductors. That's it. And we will also understand why do they start behaving like conductors. We will see that in today's class only, if time permits and we are able to move fast enough. We understand these insulators and semiconductors and conductors. Note it down fast, 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 fast. Everyone has noted this down?
Noting, sir.
Okay. That takes us to the next heading. Shall we move on to the next heading? Huh? Now we are still writing what is conductor and what is insulator. Noted it down?
Yes, sir.
Okay. And the next thing that comes for you is known as current density. And this, gentleman, is a vector. Current density is a vector. So, what is current density? It is current per unit area. Current density is current per unit area. But it is a vector quantity. If you divide current by area, both are scalars. You will not get a vector quantity. So it is a vector quantity. And therefore it must have the direction. What is the direction of current density? Yeah. Direction of current density is
Same as current, sir.
same as current, sir. Well done, sir. Its direction is same as current. Though current is not a vector quantity, current is a scalar quantity, but current density is a vector quantity. This current per unit area and its direction is same as the direction of area. So I can write this, gentleman, like this. J vector is di by dA, and the direction is in the direction of current. If you want, you can write it in this way. If you wish, you can write it in this way. di by dA, small current divided by small area, and the direction of this current vector is same as the direction of current. If you don't want to write it like this, you can also write it like this. Oops. You can also write it like this. I hat. You understand meaning of I hat? Here I is not that xi wala I. This I is a vector in the direction of current. Do we understand this? It
Yes,
might
sir.
create a doubt. That's why I don't use this I hat. Therefore, I use this eta hat. Understand? Because I hat might remind you of x, y, and z axis, and that is why I use this eta hat or eta vector. So far, so good. It is going into our heads or it is going out of our heads, saying bye bye. Bye bye, sir. I'm going. Bye bye.
Understood, sir.
Ah, your understanding is very dangerous. You understand it today, and 5 minutes afterward, you will forget what you have understood. Now, this is a revolutionary diagram that is going to tell you how current and current density are related to each other. I have taken a small cross section here, small cross sectional area, small cross sectional area dA. Current is moving like this from left to right, as you can see. Current density is also from left to right, and you can see the direction of these three vectors. Current is not a vector though. The direction of these three quantities, they are in the same direction. Do we understand this? Yes or no? No, yes, huh? Huh?
Understood, sir.
Understood, sir. So from here, I can also find a very revolutionary relation between current density and current. If I have this small area, I hope you can see this small area. Yes or no? Every area has something known as dA vector. Do we remember this dA vector?
Yes, sir.
What was this dA vector? Huh? Allu Arjun or Amitabh Bachchan?
Area vector, sir.
Both starting with A.
Area
Not
vector, sir.
area vector. Okay. Area vector it was, not Allu Arjun and Amitabh Bachchan. Okay. And this is your current density vector, J vector. Both of these are inclined at the legendary angle theta. Legendary angle theta. Then I can relate this J vector, dA vector, and theta with current. Can anyone tell me? Current is a scalar. Current density is a vector. Area is a vector. Theta is the angle. That should remind you of something that we had done some 15, 20, 15, no, not 15. Yes, 15 classes ago. Sir, we don't remember what we had done 15 minutes before, 15 classes ago. That is 15, 20 days ago. What will we remember? Yes or no? What will we remember, sir? Your legendary current can be written as J dot dA, or it can be written as J into dA into cos theta, where theta is the angle between J and dA. Again, I will ask you the same question. Does it remind you of something that we had done previously? I know that you don't remember. And your favorite hero is Amir Khan. And your favorite movie is Gajini. But still, hoping against hope. Does any one of you remember? Something like this existed a long time ago. Yes? Something like this existed long time ago.
Yes, sir.
What was that?
V equals to dr cos theta. V equals to dr cos theta.
E is equal to VR cos theta. Okay. E is equal to VR cos theta. E is equal to VR cos theta. Anything else? E is equal to VR cos theta does not exist in this universe, at least. Might be from some other parallel universe, not in this universe. So think about something from this universe. This is a good universe to live in. This is a very good universe. You see, 4% of what we see. It's a wonderful universe. This is from your favorite topic that you kept on telling me, sir, start from there, sir, start from there, sir, start from there. But sir was stupid. He started from the very first beginning of electrostatics. And this is what? Something known as Gauss law, area vector. The only place where we use area vector was Gauss law. Gauss law was 15 classes back, sir. 20 classes back. How could I remember? We are Gajnis. We can't remember that one. Sir, don't expect us to remember it. This is so unfair of you to remind us of something that we did 15 classes back. We still don't remember the name. How are we going to solve the question which is going to come exactly after 15 days from today? Not chances are very slim that we'll be able to solve the question on Gauss law if you don't even remember what Gauss law was or where you saw this area vector stuff. Anyways, I have started my prayers for you. Every day I pray to God. Please help them. And I am very sure that on the day of exam, Saraswati Maiya is going to come in different avatars, in different examination centers around Hyderabad, Telangana, everywhere, where my students are sitting, and they will bless you with good knowledge. And with that knowledge, I'm sure you are going to clear the exam. I have full faith in that. Trust me. I have full faith. Anyways, coming back to this universe, back again, the same thing that was there. Electric flux, we have forgotten that, but that was something known as phi. Electric flux, phi, was E dot dA, and flux was a scalar quantity. It was the number of electric field lines. What was electric field? Okay, there was something known as electric field that we studied some classes back. Some charge creates electrostatic field. There was something known as charge, something known as electron, proton. They were creating electric field. Because of that, they were experiencing forces. So there was something called electric field. And because of that electric field, there was something known as electric flux, which was the total number of electric field lines which was crossing through a given area. Same is the case here. This current represents the total number of charge that is flowing through a particular cross section. And your current density is the number of charge flowing per unit area per unit time. Electric field was number of electric field lines per unit area. And your current density is number of charges per unit area or current per unit area per unit whatever. So I can think it of in that way because it's the same thing. This is how a vector gets converted into a scalar with a dot product. And for your kind information, that was not E is equal to dr cos theta. It was the ulta of that actually. Anyways, that was the ulta. So we are in a probably a universe with negative mass, antimatter universe we are there. So everything looks ulta to us. Come on, this universe. This is a good universe to live in. So I'll give you time, 2 minutes in this universe. So please note this down and please go back and see what we had done in Gauss law. I hope that entire exercise did not go in vain. I give you 2 minutes to note this down. Have you noted it down already? While I was describing the 4% of the universe, have you noted this down? Good. If you noted it down, that is great. Noted?
Nothing, sir.
Noting down. Okay, note it down. I'll give you time. I'll give you time. Note it down. Once you are done, please let me know. You have completed, and I hope some part of it you will be able to recollect 15 days from now. Not 15 days, 15 plus 4, 19 or 20 days. No, more than that probably. I hope you will be able to recollect it. I seriously hope that you will be able to recollect it. Anyways, that was the relation between what? Current and current density. Current and current density, and I have written this slightly wrong. I cannot write it as full current I. I should write it as small current Di. So that is the one mistake that I have made. Di, small current Di. will be J dot dA, and I have to correct everything. Small current DI will be J into dA into cos theta. That is how I must write it, so that I can write the full current as integral of J into dA into cos theta. This is the vector, the new vector that we have come across, and that is your current density vector, the only vector that we will come across in this legendary chapter is this current density vector. Now there are some things that you must remember about this current density vector, because it may come to you in the examination hall if you can recollect it, obviously. What is the type of quantity it is? It is definitely a vector quantity. The SI unit is ampere per meter square, and its dimension is L to the power minus 2 into A, where A is ampere and not area. Please remember, A is the dimension of current, which is ampere. I hope we understand this. Yes or no? No, yes?
Yes, sir.
Good. Let me see if you can do this question based on what we have studied till now, and I have high hopes that you will not let me down. So this is the first question that comes to you: a beam of electron traveling with a speed of these type of questions are coming in the exam these days, and therefore I am hell bent on doing these questions, because I feel that at some point in time these questions are going to come. So this is the first question in this line. A beam of electrons moving with the speed of 10 to the power 6 meter per second along a line produces a current of this much. Find the number of electrons in 1 meter of the beam. I'll give you 1 minute to do this. Option B, 10 raised to the power 7 is correct. Well done. So how do you got to do this? Current is charge per unit time. Just have to divide it by time. And how do I find out the time? It is very simple. You can do it by current is Q. Electrons is there, so you know the number of charges, the charge of an electron. Uh, so we are back with a bang. Bang, 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 back with a bang, 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 bang. Okay, so charge, you know, is 1.6 into 10 raised to the power minus 19 divided by time. Time you can write it as x, distance travel, divided by velocity v. So velocity v can be written here 10 raised to the power of 6 multiplied by the number of electrons that are moving through it. Do we understand this? Yes or no?
Yes, sir.
From here, we can find out the value of n by x. The value of n by x will be simply I, and the current is already given to you. How much is the current given to you? 1.6 into 10 raised to the power minus 6 divided by 1.6 into 10 raised to the power minus 19 into 10 raised to the power 6, and I think from here you should be able to get your answer if you divide it correctly, and I think the answer is going to come as 10 raised to the power 7 electrons. Do we understand this, everyone?
Yes, sir.
Well done. My hopes have come alive. The only thing that is a problem with you guys is you forget, and that is not a good thing, beta. In your life, that is not a good thing. And I hope that you can do a quick revision. Can you do a quick revision? Yes or no? You have made your notes. Yes or no? Huh? We have made so many notes. Have you made those notes? Yes or no?
Yes, sir.
Yes, sir.
Okay. Hope is alive. This one is the next one. Lots of questions have come on this, and I have told you that. A beam of electron moving at the speed of in a Bohr's model of hydrogen atom, electron revolves around the nucleus in a circular orbit of 5 into 10 to the power minus 11 meters. Its time period is 1.5 into 10 to the power minus 16 seconds. These are approximately equal values, approximately the exact values. What is the current associated with that charge? It's moving quite fast. That's what I can tell you. Yes, my dear friends, do we have an answer for this one? It's a very simple question. Should not require a lot of theatrics. I'm still waiting. No answer? Not a good. Not a good sign. Shall I do it?
One second, sir. One second.
Answer is?
Doing, sir.
Your doing, sir, is taking too long, sir. I'd already given you the formula, sir. You just had to apply the formula, sir. And the answer comes, sir.
Option D, sir.
Option D, sir. God exists. I. When electron is moving in a circular orbit, I gave you the formula Q by T. You just had to divide. Charge of an electron is 1.6 into 10 to the power minus 19 coulombs divided by the time period 1.5 into 10 to the power minus 16 seconds. As soon as you see this, you have your answer as option D. It should not have taken so much of time, beta. It was straightforward division of Q by T, nothing else. Do we understand this?
Yes, sir.
Time period was given. We understand this, everyone?
Yes, sir. Understood, sir.
Do it fast, na beta. These questions are going to come in your exam. You have to do them quickly. We can't spare much time on this. Next one, give me the answer fast. This one. An electron is moving in a circular path of radius 1.5 something something, frequency something something. What is the equivalent current? One of this question is going to land up in your papers. One of these. Think it of as this question is in your paper. JEE Main 2023, first attempt, January, between 24 to something, 31st, I guess. Yes, what is the answer? Any hope, or shall I do it?
Doing, sir.
That is Chalo, we got the answer for this one. How we got to do this? It is as simple as it gets. I is equal to Q multiplied by F. You just had to multiply this. So the charge of the electron is 1.6 into 10 raised to the power minus 19. You just multiply it by 6.8 into 10 raised to the power 15 and you end up with your answer. Remember, this radius is just given to confuse you. You have got nothing to do with this radius. Do we understand this, or this has gone above our head saying bye bye?
Understood, sir.
Next question, sir, comes on your screen, sir. Now, sir, question number 4, sir, or 5, sir, or whatever, sir. Let's see who gives me the answer for this one, sir. I'll give you 2 minutes to do this, sir. Let me know once you are done, sir. Yes, sir. What is the answer, sir? Yes, sir. Which one is the answer?
Option C, sir.
Option C, sir. Well done, sir. But this is not the answer from this universe, sir. From some other universe, this is the answer. In this universe, the answer is different, sir. Yes, can anyone tell me the answer from this universe?
Option B, sir.
Option B is the answer from this universe. Congratulations to those who are in this universe still. And those who have wandered to a different one, please come back. This is a good universe to live in. V is equal to IR and F is equal to MA is valid. So how got to do this? Current density J is current per unit area. We just now saw this. We have a copper wire of length 1 meter and radius 1 meter. Is joined in series with a iron wire of length 2 meter and radius 3 meter. Remember, this current density is proportional to I. These two wires are joined in series. Therefore, I is same. Do we understand this, sir? Yes, sir? Or no, sir?
Understood, sir.
Yes, understood, sir. I is same, sir. So current density is inversely proportional to area, sir. Length does not come in the picture, sir. So I can write current density in copper divided by current density in iron will be area of iron divided by area of copper. That will be equal to, now area of a conductor. Remember, a conductor is like a cylindrical wire. And this conductor, you understand the conductor? The cylindrical wire, this area is the cross section area of the conductor, sir. Do you understand this, sir?
Yes, sir.
And that is equal to pi r square, sir. So this will be the radius of iron divided by radius of copper ka square, sir. You understand this, sir?
Yes, sir.
And the area and the radius of iron wire is 3 times, sir. 3 mm, sir. And therefore the correct answer is 9:1, sir. You get this, sir?
Sir.
Length has got nothing to do with current density. You understand it?
Yes, sir.
Ah, comes the next question, and the same question came in JEE Advance of this year, sir. Last year, sir. Not the exact question, but a question based on this. You have to find out the current in this conductor. This is a simpler version of the same question, and the version is here, sir. This is the version that I am putting here. This is a simpler version of the question that appeared in your JEE Advance, sir. And if time permits, sir, I can show you that question, sir. Where is that question, sir? I am finding it out, sir. But your question is simple, sir. You can give me the answer to this while I am roaming around here and there, sir. Yes, sir. Wow, sir, I got a very good question also, sir. Yes, sir. No, sir. Answer, sir. No answer, sir. Am I looking at an answer, or I am just looking to chill out? with you guys, which I will after your exam. I'll come and chill out. Yes. Eh? So much we have to think, sir. So much, sir. So much, sir. The
Sir,
question
option
is very
C.
simple, sir. Oh, sorry, sir. Drift speed we have not read up till now, sir. So we cannot solve this question, sir, right now, sir. I did not see whether this question was of drift speed, sir. So my apologies, sir. We cannot solve this question, sir. Uh, I can change this question to this thing, sir. Instead of writing it as drift speed, I can write instead of drift speed, you use current, sir. Current, sir. Current, sir. Current, sir. And now give me the answer, sir. Sorry for the small correction. Now give me the answer, sir.
Sir, option B.
Option B, sir. The current increases from A to
Yes, sir.
A, sir. So I've got two answers, A and B. Which is the correct answer?
Option A, sir.
Option A, sir. Because current in the conductor remains constant, sir. But something changes, sir. Can you tell me what is changing here? The next part of the question, sir.
Current density, sir.
Current density, sir. Well done, sir. Where current density is more, sir, and where current density is less, sir? Where is current density more, sir, and where is current density less, sir?
At A, current will be more, sir.
At A?
Current will be more.
Arey, Dada, please come back in this universe, bacha.
I'm chap-
Current is same,
Yes,
sir.
sir.
Current density is more at A and current density is less at B. Do we understand this, sir? You said current, sir.
Current density, sir.
Current density, sir. So in this universe, current density is different than current beta. Stay in this universe. And as promised, this was the question that came in this year JEE Advanced, sir. And I'll give you this question just because this type of thing has come. This was a question from your JEE Advanced, sir, of this year, sir. This is a question based on a balanced Wheatstone bridge. You understand a balanced Wheatstone bridge, then there is a meter bridge connected. Doesn't matter. This A to B that you see here, this A to B that you see here is not a uniform wire. This A to B is not a uniform wire here, sir. This wire is in the form of a frustum of a cone, sir. And now I should not use bigger terms like this, but this frustum of the cone, sir, looks like this, sir. This frustum of the cone looks like this, sir. And you must remember the resistance of this thing, sir. This is the exact question, sir, that we have done right now, sir. You have to remember the resistance of this question, sir. What is the resistance of this frustum of the cone? If you would have known that resistance, you would have actually done this question pretty simply, sir. So as I keep on telling you, sir, that there are things that you will have to remember. It's not important that you actually solve a question and get the answer, sir, but what is important that you know how to use the result of that question, sir, in any question that comes in the exam, sir. Do you understand what I am saying, sir? Or it has gone above your head, sir? Do you understand what I'm saying? You will have if you did not remember if you don't know the resistance of this wire which has a non-uniform cross section, there is no way in
Sir,
the
sir,
yes.
sir, can you repeat again, sir? Sir, we have an echo, please, sir. We could not hear your voice.
I was telling you about the question that came in JEE Advanced, and the question that came in JEE Advanced was, you saw that question? This was the question that came in JEE Advanced. And here this wire A to B that you see is not a wire of uniform cross section. It's a wire of non-uniform cross section that had come in that question. And the only thing you had to find out was the resistance of this wire, and you cannot find out the resistance of this wire unless you know this formula. So you had to know this formula to do anything about this question. And trust me, to derive this formula in the examination hall would have been almost a very difficult task. But if you would have been careful enough, you would have done. And I would therefore tell you that question that you should have done to get this question. And I always give my students this question as a question that you must remember as a standard result. And what is that standard result that you must remember? Oops, why is not going up? I will have to delete this. I will have to delete this. Okay. So I always tell my students to remember this standard result of this question. And this question is not a new question. This question is a question that has been repeated from your favorite book. And your favorite book happens to be SCV. So this is a question from where this question of JEE Advanced had come. And I always give students, I'd never solve this question and find out the resistance of this wire, because that is not going to be asked. What you have to remember is what is the actual resistance of this wire. You don't know how to do it, doesn't matter. As you see, the question in JEE Advanced was, they were not asking you the resistance of the wire, calculate the resistance of the wire. No, they were not asking you that. They had made a question based on that. So you have to remember what were the resistance of this wire and the resistance of this wire. This is question number, which one? Question number 10 from your SCV, given on page number, what page number? Page number 198. Okay. So something has happened. I will just take it off. Okay. So what matters is you remember the result. If you don't remember the result, you cannot solve the question that eventually comes in the exam. Do we understand what I'm trying to say here? So I tell you all these important points. Why do I keep on telling you all these important points? Is because one of these points is going to come in the exam. But in the case of JEE Advanced, it will not be a direct question. JEE Advanced will not ask you the resistance of this wire. They will make a question on that. And that is how questions come. We got this, what I wanted to say? Yes or no?
Yes, sir.
Got the essence of it? I will solve that question of that JEE Advanced, and it's very simple. You just have to find out the ratio of resistance. It's a meter bridge. It works on the principle of a balanced Wheatstone bridge, nothing else. I've already told you balanced Wheatstone bridge, and there's nothing in a meter bridge that you have to know that you don't know. So if you just remain patient and you just do things that I have done in the class, there is nothing that is remaining. I was looking for this question. I found a different question which came in your JEE Advanced, and again I'll show you that, and you will see and you will see that I had no idea that this question had come. I had actually forgotten. I don't remember questions of very recent years because I hardly see their papers. But see, this was the question that came in this year's JEE Advanced, and you will understand that I have done too many questions based on this. Where there is a dielectric, it is a capacitor, it is filled up with a dielectric connected to the battery, then the plates are moved, something. You just have to find out what all things change. You can do it, yes or no? Same questions we have done, so many questions we have done, yes or no?
Yes, sir.
See, If you just remember simple things, in this case, battery ka voltage is going to remain constant. In this case, the battery ka voltage is V. You can find out the electric field between the two terminals, V by D. In this case, what they have done, they have changed the distance. So voltage will remain same, but electric field will change. Yes or no? Then they have asked how much does the capacitance change. You can find out the capacitance of this arrangement. You can find out the capacitance of this arrangement. See, this is a multiple choice question in JEE Advanced, which is the most difficult question of a JEE Advanced. Do you understand what I am trying to say here?
Yes, sir.
Just have to concentrate on what we have done in the class. I feel very sad when you just don't remember what we have done in the class. Now, if this question comes and I tell you that I have done this question in the class, it is wrong. If I claim that I've done this question in the class, will it be wrong? Obviously, I will not be putting up the exact question, but I'm not the one who makes the JEE Advanced paper. But we have done too many questions on this type. Moral of the story is where I was. Moral of the story is, if you just remember simple things, you should be able to do even the most difficult question that come. Have you understood this question?
Yes, sir.
Have you noted down the resistance of this wire?
Yes, sir.
Okay, we have not come to that part where we calculate resistance, but since this question had come up and therefore it was essential that I tell you all those things, we are still dealing with what? We are still dealing with current density and current, and I hope we have done enough on this. It is not required anymore, so let us move ahead and move to the next topic. And I can just give you this small thing. Should I give you this or should I give you that? I can write this heading then. Motion of electrons inside a conductor. Motion of electrons inside a conductor. I'm saying you can write it. I know that you can't see it. Trust me. Motion of electrons inside a conductor in the absence of electric field. Absence of electric field. Now, there is a very simple question that used to come in my mind when I was studying electric field in your time. I did not have teachers to teach me that. I mean, what is a conductor? A conductor is a body which has a large number of free electrons. What is charge? What is current? Current is the flow of electrons. Now, if this conductor has a large number of free electrons, even if this conductor is not connected to anything, there is no battery, there is no EMF, there is no electric field, even then it should have current. Why it does not have current? It should have some current, may not be large, but it must have some current. Yes or no? Must have some current because there are a large number of free electrons. These are the electrons. When you apply electric field, they start moving in opposite direction or reverse direction or whatever it is. But even if there is no electric field which is applied, there is no potential difference which is applied, still there must be some current. Still the electrons are moving. Yes or no? Huh?
Yes, sir.
That velocity can be known as the thermal velocity of the electrons or the RMS velocity of the electron. Now, this word RMS might ring some bells. Is it ringing any bell? No, sir. What is RMS? I don't know RMS. Is it ringing any bell, this RMS velocity? Huh? So we can write that as a thermal velocity or the RMS velocity. Now, this velocity of electrons, now this thermal velocity of electron comes because of the random movement of these electrons and because of the temperature of the conductor. The conductor is not at 0 Kelvin. The conductor is at room temperature. Room temperature is quite high compared to 0 Kelvin. So these conductors, the electrons in these conductors are moving with a velocity. You can call that a thermal velocity or thermal speed. You can also call it the RMS speed. How will you find out that RMS speed? Huh? Obviously, we don't know. So it will be like this: half mv RMS square. The mean kinetic energy of the electron will be 3 by 2 kT. Does this 3 by K2 ring any bell in our brains? 3 by 2 kT, what is that? I don't know. Does this 3 by 2 kT ring any bell?
Sir.
What? We had done it in a chapter which was known as thermodynamics, where we were dealing with not the velocity of electrons, but with the velocity of atoms and molecules of the gas. Yes or no? The same thing here. It's the same thing here. So from there I can find out the thermal velocity of these electrons, and the thermal velocity of this electron will come as 3 kT by m, where k is our old friend, the Boltzmann constant. This is a Boltzmann constant, and at room temperature, which is taken as 300 Kelvin, 27 degrees Celsius, something of that nature, this velocity comes equivalent to 10 raised to the power 5 meter per second. With this much velocity, even if there is no battery connected, these electrons are moving. So there must be current. Yes or no? Huh?
Yes, sir.
So that is good, na? I mean, I don't need any power supply. I just hold this wire and hold it in front of the laptop, and the laptop should run because there is current. Yes or no? Yes or no? There would be current. Yes or no? Anyways, this is the RMS velocity. Now, when these electrons are moving, they are colliding with each other. Yes or no?
Yes, sir.
Because there are a large number of electrons, so they are colliding with each other, and in between collisions, they are traveling some distance. Mean free path. Mean free path. Does it ring any bell?
Sir.
Mean free path of that gas molecule. This is mean free path of the electrons. Then there is something known as the relaxation time, which you have in abundance, because right now also everyone is relaxing. What is the relaxation time? Time between any two consecutive collisions is known as relaxation time. Do we understand this, bacha?
Yes, sir.
But my question still remains. Why? Why with so much velocity? We're moving so fast. Why even with so much velocity? Should there be current? Is there a current? There is no current. Why there is no current? Why there is no current? Because these electrons are just moving randomly. These electrons are just moving randomly. They are moving randomly. That means, what do you mean by random motion? Some electrons are moving like this, some are 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 like this. So their net average velocity, their average RMS velocity, average velocity of gas molecules was also, if you take a cross section, the average velocity of this, if there are n number of electrons moving in this direction, there will be n number of electrons which will be moving in the opposite direction. Yes or no? So whether you find out the average velocity of those gas molecules, that will also come out to be 0. If you find out the average velocity of these electrons, that will also come out to be 0, and therefore the current in the conductor, when there is no voltage, it comes out to be 0. Do we understand this?
Yes, sir.
So, when there is no battery connected, no voltage applied, the electrons, though they are moving very fast, the net flow of charge is 0. Net charge is 0, and therefore consecutively there is no current flowing in the conductor. Do we understand this? Yes or no?
Yes, sir.
What happens when you connect the conductor with a battery or EMF is applied? What happens when you apply a EMF or battery or potential difference? So the next heading is behavior of conductor due to PD. What is this PD? What is this PD? Huh?
Potential difference, sir.
Potential difference. So now what I am going to do, my dear friends, I am going to apply a potential difference across the ends of the conductor. I am going to apply potential difference across the ends of the conductor. Now, this is the diagram. First understand this, then write it. If I have applied a potential difference, let us say V across the ends of this conductor, let us say that the ends of the length of this conductor is L. Because of this applied potential difference, there is an electric field there's an electric field that is applied across the conductor. Yes or no? No, yes. Huh? Because of this
Yes, sir.
potential difference, the direction of electric field will be from right to left. Yes or no?
Yes, sir.
The value of this electric field, the potential difference is constant, will be equal to V by L. Do we understand this?
Yes, sir.
Now, because of this electric field, electrons will now have an acceleration opposite to the direction of electric field. So, electric field is applied in the right to left direction. Electron will now have an acceleration in the opposite direction. Yes or no? No, yes.
Yes, sir.
So the acceleration of the electrons, which will be opposite to the direction of electric field, will be equal to small e into capital E by m, where small e is the charge of the electron. Yes or no? No, yes. And the direction of this acceleration will be opposite to the direction of electric field. Are we able to understand this, or this is going above our head saying bye-bye? Huh?
Understood, sir.
Now, because of this applied electric field and because of this acceleration that is going to come into the picture, these electrons will have a velocity. They will acquire a velocity opposite to the direction of electric field. Yes or no? Yes or no?
Sir.
This velocity is known as Allu Arjun or Amitabh Bachchan. This velocity is known as, is the
Drift
same velocity which I
velocity.
cut from there and I call it current. Does anyone remember?
Drift velocity.
See, this universe is beautiful and God also exists in this universe, not in other ones. Yes, this velocity is known as the drift velocity. So that is the next heading that you are going to write just below this. What is this drift velocity or this drift speed? What is this drift velocity or this drift speed? Tell me fast. It is the velocity velocity with which free electrons move or drift towards the positive terminal of the battery. This velocity is known as the drift velocity Vd. And what is the direction of this drift velocity, beta? Huh?
Direction of current.
It will be towards the positive terminal of the battery or opposite to the direction of electric field. Do we understand this?
Yes, sir.
Definitely.
So now I can just go up and write this drift velocity will be equal to, if I write it vectorly, it will be in the direction of vector A multiplied by tau. Do you remember this tau? This tau, what is this tau?
Torque.
Torque. Hey Bhagwan. Tau. Tau. Tau, 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 tau,
Relaxation
tau,
time, sir.
tau, tau, tau is the relaxation time here, beta. Not torque. There's no need of torque now. Okay, things happen. Anyways, tau and tau is used for torque. This right now there is no torque here. This tau stands for the relaxation time. In that relaxation time, they are going to move. Do we understand this, or this has gone above our saying bye bye?
Understood, sir.
Thank you, sir. Your understanding is very very dangerous, sir. So now I can write it like this: minus E by m into tau. Very important result. Why written this negative sign? Huh? Just like that, sir. You like negative sign. Why written this negative sign? Yes. Why this negative? I always talk about positive things in life. Why this negative here? Why this negative here? Why this Colaveri D? Tell me. Why this negative sign? Why this negative G? Tell me.
Going opposite to electric field.
It is going
Opposite to electric field, sir.
It is going opposite to the electric field. That is absolutely correct. Do we understand this?
Yes, sir.
Okay, so this is your new friend. And what is the name of this new friend? Drift velocity. And because of this drift velocity, we say that the current is flowing in a conductor. And this drift velocity will only come when the conductor is subjected to a potential difference, and the value of this drift velocity, and you will be very astonished to see the value of this drift velocity is 10 raised to the power of -3 or -4 meter per second. It is not very fast, it is very slow compared to the RMS speed. RMS speed is 10 raised to the power 5 or 6 meter per second. This is only 10 raised to the power -3 meter per second. But this, because of this drift velocity, we have current, and not because of that thermal velocity. Do we understand this? I'll give you 2 minutes to note this down. These are the formulas on which they can make some questions which might look a bit out of the ordinary. So note it down carefully. I'll give you 2 minutes.
Yes, sir.
Well done, completed. Then we can move ahead. We have found out the relation between drift velocity and relaxation time, drift velocity and electric field. Now we will move ahead and write the relation between drift velocity and current. relation between VD and I. What is the relation between VD and I? We will not go into how do we get this relation. I will just tell you the relation. I is equal to N A E V D. Now you have to tell me what is this N, what is this A, what is this E, and what is this VD. Yes. What is I here?
Current, sir.
I is current. Good. What is N here? Number of free electrons. Not the total number of free electrons, but it is the number of free electrons per unit volume. In 1 unit volume, how much free electrons are there? We understand this? Okay. What is A?
Area cross section.
Area of cross section of the conductor, correct? What is E? Small e. What is this small e? What is this small e? Charge of an electron. Do we understand this, bacha? This small e is the charge of an electron, and this VD,
Drift velocity.
this drift velocity of the electron. Now, you can also see on what all factors this drift velocity depends on. On what all factors this drift velocity depends on. Now, we had seen this drift velocity can be written as oops, E by m into tau. Yes or no? I'm just talking about the magnitude. Do we understand this? Huh? That means I can write, and remember these are important points. That means I can write this VD is directly proportional to electric field. Yes or no? If you increase the electric field, drift velocity will increase. Yes or no?
Yes, sir.
This VD is directly proportional to tau. Yes or no?
Yes, sir.
If time of relaxation is large, drift velocity is large. Do we understand this?
Yes, sir.
Or no? Now, this time for relaxation tau, it depends on two factors. On what two factors it will depend on? It will depend on the nature of material. Because if you have a good conductor, a very good conductor, it will have a large number of electrons. If there are a large number of electrons, there will be a large number of collisions, and therefore the time between collisions will vary on different scenarios. Yes or no? This tau also depends on the temperature of the material. Do we understand this? If temperature rises, then what will happen? Time between collisions will become more, or time between collision will become less? temperature rises, the electrons will move faster and therefore they will collide faster. Yes or no?
Sir.
Yes, sir.
So tau will decrease and therefore your drift velocity will also decrease. Yes or no?
Yes, sir.
Remember these important things. Drift velocity is inversely proportional to temperature. If the temperature increases, drift velocity decreases. Do we understand this?
Yes, sir.
Now let us come to current. Now let us see on what all factor current depends on. Have you noted this down? Yes or no? Everyone has noted this down.
Done, sir.
Now let us talk about current. Current is directly proportional to N. More number of free electrons, more conductor, more current, better conductor, good conductor. Do we understand this?
Yes, sir.
I is directly proportional to I is directly proportional to N we have seen. The second thing will be I would be directly proportional to the area of cross section. Yes or no? More area means more electrons, more conducting electrons. Therefore, you will have more current. Yes or no?
Yes, sir.
I is directly proportional to VD and therefore it is directly proportional to E. More electric field, more electric field, more electric field, you will have more current. Yes or no?
Yes, sir.
And this electric field is proportional to V by L. Yes or no?
Yes, sir.
So that means your current becomes directly proportional to V. Your current also becomes inversely proportional to L. Are we able to understand this or this is going above our head saying bye bye sir, बहुत हो गया sir, छोड़ दो sir अब.
Understood, sir.
At the same time, this drift velocity, my dear friends, is also inversely proportional to time. So I is proportional to Vd, which is directly proportional to tau, which is inversely proportional to the temperature. That means if you increase the temperature, current will come down. Do we understand all these relations?
Yes, sir.
Or it has gone above our hands, sir. Bye bye, sir. Leave us,
Understood,
sir.
sir.
I'm going, sir. Well done, sir. Tata, sir. Hmm?
Understood, sir.
I'll give you 2 minutes to note this down and remember this for the rest of your life, at least till the exam. So I guess you have completed this. We have seen the relation between current and current density. Now the last part of this class comes up. Relation between current density and drift velocity. And it is very simple to understand this. Current density J is current per unit area. Current is NAEVD. So it becomes NE into VD. So here we have now the revolutionary relation between current density and your drift velocity. I've given you time till tomorrow to go through all of these terms because these terms are slightly new and we will do some questions where we would be able to find out the relation between all these quantities and see how current varies and different question, what is the relation between drift velocity, is this that, if this is constant. So we'll do a lot of questions in the next class. I sincerely request you, please go through this class because if you don't understand, if you don't remember what we have done in this class, the next class is going to be a waste of our time. Because everything we have done in this class is going to be applied in the next class. Do we understand this?
Yes, sir.
On that note, I will dismiss the class today. I hope you will practice this and come prepared in the class that is tomorrow. Everyone has understood what we have done in today's class.
Yes, sir.
Everyone has made notes for this class. Yes or no?
Sir.
Okay. So take care and may God bless you. Bye bye.
Thank you, sir.
Bye, sir.